Okay, so let's talk about Gauss's law for magnetic fields. And we want to show that things are very different compared to electric fields. So for the electric field, we had Gauss's law said that the integral of the electric field over a closed surface is equal to the charge that's inside divided by a number, right? So the charge is the source of the electric field. This is not going to be the case for magnetic fields because of their geometry. So we have to consider integrating the magnetic field over a closed surface, and when we do this, we're going to show that we'll always get zero. It has nothing to do with the whether there's current inside of a closed surface or not. So let's make the geometry. Let's draw the magnetic field of an infinitely long current-carrying wire. So here's the wire. Let's say it's red current coming straight out of the page towards us, and from the Biot-Savart law, we can figure out, right, dr cross r hat, or dl cross r hat. Right, this is a part of the Biot-Savart law that gives us the direction of the magnetic field, be proportional to dr direction of current cross r hat. And so dr is pointing out, and let's say we want the field to the right, then this tells us that the field there is pointing this way. Right, so that's the direction of the magnetic field. So the magnetic field is circling around. It's doing something like that. Okay, so now let's consider integrating. Let's make the calculation as simple as possible for us. We want to do this calculation. We want to integrate the magnetic field over a closed surface, and we want to do it in such a way that it's very visual. So let's integrate over a red surface, and we'll consider a tube. Right, it's a cylinder. So a cylinder that has its axis that shares this as the axis for the cylinder. So the infinitely long current carrying wire goes through the center of the cylinder. So the cylinder is placed such that, if we look at it from this perspective, things look like this. The field on the edge of the cylinder looks like this, and we integrate that. So if we look at it slightly tilted, so here is the current. So if this is the current I naught, say, then our surface, our cylinder looks something like this, where the current continues to go this way, and we're going to close it off at some point, and it will look something like that from that perspective. The wire continues this way. So the field circles around, so the field here would be pointing like this. Right, so on this part of the cylinder, the field is pointing like that. Those are some field lines. And here we'll have, just like here, we would have a larger field because we're closer to the source. Larger field here circling around. And that would look like something like that here. Okay, in the back there as well. So we integrate over this cylinder, and that basically means that we have to integrate over the part that has a curved embedding here, right? The part that, if we cut this and open it up, it's a rectangle, right? I can turn a rectangle into a cylinder, right? So here's my rectangle, and I can turn it into a tube part. So when we integrate over this part, right, the current carrying wire goes straight through the middle here. right? The field is lying on the surface of this part here, and so there's no contribution to the flux. None of the field lines go through that surface. So if we draw the DAs, right, the DA here is normal to the surface. The DA here is normal to the surface, right? We always have 90 degrees. The same is true here, so maybe we can look at it from this perspective. The B field here is pointing that way, but the DA is pointing towards us. So here is the direction of the DA. The same is true here. DA is pointing outward, so we have 90 degrees between B and DA. And so we do the dot product, and therefore it's a cosine of 90. That gives us 0. So on the edges, there's no contribution to the flux. The magnetic field lines are not going in or out through this area here. Same thing on the back disk, and it's true here as well. So we made the calculation easy for us, but it would be true regardless. So if we change the orientation of the cylinder, or we use any other closed surface, here's the tube, here's the closed cylinder. All right, so we close the top and bottom, and we put it over there. It would still be true that the total magnetic flux through this would be 0. There would be places where the field lines come in, but then there would be places where they come out, and the net contribution would give 0. So this is what we get. We can see that in a simple situation like this or this, but it's true more generally. And the reason for this is that magnetic field lines don't start at the source. They don't start anywhere. So you can follow a field line and you can end up back at that same field line. And so when you have a closed surface, you'll get field lines coming in and coming out. So just to parallel this with the electric field case, right? So Gauss's law for electric fields says that, notice that it's the same thing when you have, say, some charge Q naught that produces an electric field, right, that diverges radially away, something like that. And we consider, say, a closed surface that is maybe a cube or a box or something like that, right? You'll have field lines that come in at some point, and then they have to come out. It's not obvious why there would be a net cancellation, but it's the same idea. Right? You don't have a net charge inside, and so the field lines will come in somewhere and come out somewhere else, and overall the flux will cancel to 0. But if instead you place the closed surface such that the charge is inside, so here's Q naught, then the field lines will only come directly out, and no field lines go in from the outside, and so there's a net positive flux. And so in a sense, you can just follow the field, and there's no way that you can generate a situation where the field lines come only out of a closed surface for magnetic field lines, because magnetic field lines don't start anywhere, unlike electric field lines. Okay, so we're going to explore these concepts a little more deeply.